a higher order derivative? Rich. Let's say I have y equals 5x to the 6th plus 2x to the 4th minus 7x to the 3rd plus 5x. And I say, what's the derivative? Okay, x to the 5th, good. Plus 2 times 4, 8, x to the 3rd, 21x squared plus 5. Not bad. But the topic is higher order derivatives. What does that mean? If I want to find the second derivative, that's the derivative of the first derivative. So what's the second derivative here? What's the derivative of this answer now? 150 x to the 4th plus 8 times 3, 24x squared minus what? 42x. If I want the third derivative, 3 slashes. That's the derivative of the second derivative. 600x to the 3rd plus 48x minus 42. If I want the fourth derivative, I'm not going to put 4 slashes anymore. After 3, they don't put slashes. If you want the fourth derivative, they go y parentheses 4. When you see that notation, that means the fourth derivative. After 3 slash, the maximum you see for slash is 3. After that, just forget it. They're not going to put 4 and 5. So this will be what? 1800 x squared plus 48. The fifth derivative. 3600x. The sixth derivative. 3600, and the sixth derivative and seventh and after is what? 0. So you can take the second derivative, the third derivative, the fourth derivative. If you want to use the other notation instead of slashes, if you want to use dy dx, this one will be written as dy dx. The second derivative is written different. It's d squared y dx squared. Notice where we put the squared. Here next to the y on the top, here next to the x, top of the x. The third derivative, d3y dx to the third. d4th y dx to the fourth. d5y dx to the fifth, and so forth. You get the idea, I think. The notation is always dny dx to the n. That's the notation we use for higher order derivative. So where we use second or first order derivative? Good news, physics. We use that. Remember, I probably mentioned that last time. Velocity is change in position over change in time. That's a derivative. So if I gave you the distance or the height of an object, S is the height of a ball here. And the ball is actually, let's say it's falling down to the ground, but not, maybe it's not on the ground, maybe on the moon or somewhere, because gravity is different there. Negative 0.8 t squared plus 2. That could be the moon. Because the gravity on the moon is what? A little bit about 6. Yeah, 6. So take acceleration on the Earth, which is 9.8 divided by 6. It should be a little bit higher than that. It's not even the moon. Yeah, a little bit more than, will be about negative 1 point something. So somewhere in space there, the height of a feather, if you drop in a feather, there's no wind in space. So if you drop a feather, or you drop a hammer, or you drop a basketball, they're all going to hit the ground at the same time, vacuum. So let's see, dropping a feather. So that's the height of the feather as it falls down. If you want to find the velocity of the feather, it is the derivative of the distance or the height. And the velocity of that will be what? Negative, what do we have? 1.6 times t. If you want to find the acceleration of that planet or space where we're testing it, the acceleration is the second derivative of the height, or the derivative of the velocity, which will be what? Negative 1.6. That could be the moon, actually. What's 9.8 divided by 6? 1.6. Is it? It is 1.63. Yep. So that's probably was an equation came somebody dropping something on the moon. So the velocity is always the derivative of the displacement, the position, the height, and the acceleration is always the derivative. Remember, the reason that's the case, velocity is actually the change. I'll just do it here. Velocity is the change in the position over change in time. And if we take the limit as delta t approaches 0, like 2 points close to each other, that's the derivative. And acceleration is really the change in velocity. So it's the derivative of the velocity, which is, the velocity is the derivative of this, so that's why it's the second derivative. So the acceleration is always the second derivative of the displacement and the velocity. Make sure you know that. You probably see it on the homework. You'll be doing a problem, you'll see some on Earth, it says somebody fired a basketball up in the air, and here we go, the equation, negative 9.8 t squared plus 150t plus 75. I'm just making that up. That means give an initial velocity of 150 meters per second, flying.
75 is the height.
75 is the height of the building, yep. So on top of a building like 10-story high, you fire a ball at a speed of 150 meters per second. That's about 350 miles per hour up in the air. So it's going to go up in the air and come back. Now, the velocity of the ball at any given time now will be the derivative of that. The velocity will be what? Negative 19.6 times t plus the 150. And the acceleration, actually I gave it the wrong, so it should be 4.9 here, not 9.8. Half that number, if I want to stay with the Earth. So that'll be what? Negative 9.8 and what is the acceleration? It's the second derivative, or the derivative of the velocity, which is what? Negative 9.8. What the negative tells me is what? The acceleration is pointing where? Down. Down is negative, up is positive.
So for that question on homework, is it going to say find the derivative of...
Nope, it won't say derivative. It says find the, they might say to you, find the velocity at 4 seconds. So now you know what the equation for the velocity here, if I'm using this one. So I'll go and let t be that 4 seconds. That'll be negative 9.8 times 4 plus the 150. Find the acceleration at 20 seconds. Hopefully the thing's still up in the air for 20 seconds. The acceleration does not depend on time. What's the acceleration? Always negative 9.8, as long as what? As long as the ball didn't hit the ground. If it hits the ground, what's the acceleration? Nothing. So you need to find out when does the ball hit the ground. And see how long would it take. So if I just gave you what's the acceleration in 20 seconds, if you just go negative 9.8, you could be wrong. Because how long was that basketball or was that ball, the rock, whatever it is, in the air? Well, to find that, you take the height and you set it equal to what? 0. So how long was it in the air? That's the question here. You take the height and you set it equal to 0. As long as the height above 0, the ball is still in the air. Once the height hits 0, that means, oh, it hit the ground. So if the 20-second happens to be now more than that time it was in the air, then it's going to be a 0 there. So let's solve this one. Minus b, quadratic formula there, plus or minus the square root of 150 squared minus 4 times negative 4.9 times the 75 divided by 2 times negative 4.9. And that will tell me how long was it in the air. And you'll see problems like these, guarantee you. What's that number? That number is 23970. I don't trust myself with the calculator. I can double check the numbers. I'm horrible with calculators. Take the square root of that number, 154.8. We have two solutions. One doesn't make any sense because the time will never be negative. And the other one that's a negative. That's a negative 0.5 out of the question. Time can't be negative. That's the time here. This one, the time is going to be what? "31 seconds. So we're good. The ball was in the air for 31 seconds. So what was the acceleration then at 20 seconds? Negative 9.8. If I say what's the acceleration at 40 seconds or 33 seconds? 0. The ball already hit the ground. Okay. We're done with 3-3. That's our plan for today.